Bonjour à tous, je m'appelle John O'Reilly, j'habite à Galway dans l'ouest de l'Irlande et je travaille pour une compagnie anglaise qui s'appelle Kotlin Technology. Et c'est un plaisir d'être ici à Android Makers à Paris aujourd'hui. Maintenant, anglais. Hi folks, my name is John O'Reilly. I'm based in Galway in the west of Ireland. I work for an English company called Kotlin Technology, and it's a pleasure to be here at Android Makers in Paris today. So we're going to talk today about various patterns and capabilities that we can apply when using Kotlin and Compose Multiplatform on iOS. We'll start by giving a basic introduction to the ecosystem and talk about the default Swift Kotlin interop we get out of the box. This has a number of limitations, and then we'll cover the capabilities that the Sky framework provides to address those. We'll touch on the new Swift export functionality that JetBrains is developing to improve that interop. Next up, concurrency. Again, we'll talk about the limited interop support we get by default, and then the third-party solutions we can use for this, including use of Swift in shared KMP code is something we often need to do, and we'll demonstrate some patterns for how that can be achieved, along with some other interop options available to us for accessing native capabilities. And similarly then for Compose Multiplatform, showing, for example, how we can include use of Compose in SwiftUI and vice versa. We'll cover background work on iOS, some of the KMP, CMP testing options available to us, and a few items related to developer experience. We'll finish up then with some info on build, packaging, and publication, again focusing on iOS aspects of this. So starting off with a few basic definitions. This is how KMP is described in the official docs. It's basically providing a mechanism for writing shared Kotlin code that can be built and run natively on a variety of platforms. So first show of hands, how many people here have used KMP? Okay, wow. It's fantastic to see, I think in every talk, seeing the increase in number of people using it. Next up, Compose Multiplatform. This is a declarative UI framework for sharing UI across multiple platforms, based on Kotlin Multiplatform and Jetpack Compose. And another small show of hands, how many people using CMP, Compose Multiplatform? Okay, and how many people just using, but using Jetpack Compose on just Android? Okay, as expected, a few more using that right now. Just to mention this point, that many of the samples shown today, or many of the examples shown today, are taken from various KMP samples. KMP and CMP samples I've been working on, along with other folks, over the last 5 years or so. These all include iOS clients, and all have varying degrees of use of shared Compose Multiplatform UI. Collectively, they cover a range of different code sharing scenarios. I'll also touch on some examples we're using in a Compose Multiplatform application we're developing at Kraken. So with KMP and CMP, we have an almost continuous spectrum of code sharing possibilities. I wanted to show here a few points along that spectrum. On the left, we have a small amount of shared KMP code, along with a SwiftUI client and Swift view model, for example. In the middle case, most of the logic is shared, including the view model, with potentially some shared CMP UI code, maybe a particular screen or some part of a screen. And finally, on the right, we're sharing most of the code, including UI using CMP, with potentially some SwiftUI needed. It's important to note that our interop requirements vary considerably depending on what point along this spectrum we're targeting. So we're going to focus now on the development of iOS apps using KMP. And a key component of the Kotlin toolchain that supports that is Kotlin Native. It's described as a technology for compiling Kotlin code to native binaries, which can run without a virtual machine. It includes an LLVM-based backend and a native implementation of the Kotlin standard library. It also importantly provides bidirectional interoperability with Swift and Objective-C. You can both use Objective-C frameworks and libraries in Kotlin code, and Kotlin modules in Swift Objective-C. And what this typically means in an iOS project is that an iOS framework is generated from our shared Kotlin code. And that framework can be consumed then in our Xcode project, for example. Also an important aspect of the solution is that interop is, between Swift and Kotlin is based on an Objective-C bridge. This is an evolving area, and with the development of Swift export by JetBrains, we'll hopefully soon have direct Swift Kotlin interop. In most KMP projects, we'll need to access platform-specific capabilities, and a key component for allowing that is the expect actual mechanism. We can expect a particular API, etc., to be available in common platform-agnostic code, and provide then the necessary platform-specific implementation of that. And how we manage that then is through various source sets in our KMP modules, with common main for our platform-agnostic code, and then platform-specific source sets for each platform. So first, small expect actual example. Here we have a get country name expect function that we can invoke from the common main code. And then we have actual implementations for Android and iOS in their respective source sets, using locale on Android and nslocale on iOS. So a quick random spot quiz. Anyone here know what the ns prefix stands for in the nslocale API we're using here for iOS? Yes, exactly. So a little aside, after Steve Jobs left Apple in 1985, he founded a new company called Next, which developed the Next Step operating system. In 1997, Apple acquired Next, along with getting Jobs back, and that OS ultimately became the basis for what would become Mac OS, iOS, etc. And find it interesting that today we see that legacy manifested in Kotlin KMP code. So back to our regular schedule program, another expect actual example, this time showing how we can create platform-specific dependencies when using the Coin DI framework. We have a common Coin module, and then a module specific to each platform, again using expect actual. In the iOS case here, for example, we define platform-specific dependencies for Ktor, data store, and room. And this is how that create data store is implemented. The specific details aren't too important, but just to note again, we have access to the likes of NS File Manager to allow us to interface with the iOS file system from Kotlin code in iOS main. Also important to note that we can use the same approach for compose code, as we'll see in more detail later. Here we have this ISS map view expect function that we can use in common main compose code, with actual implementations then for each platform. The default and ideal is to have any shared iOS-specific code in the iOS main source set in our KMP module. We'll be talking, of course, about some cases where this isn't sufficient, but important to note that Kotlin Native comes with a large set of pre-compiled or pre-imported iOS system frameworks that we can call from Kotlin code in iOS main if needed. So we're going to give a few examples of some of the default Kotlin Swift type mapping we get when using Kotlin Native, again through that Objective-C bridge. Class in Kotlin maps to class in Swift, and interface mapping to protocol. And interop using these is quite seamless. Where we start to see some disconnect is with sealed classes, for example, with some functionality lost in the default mapping to a Swift class, for example, exhaustivity checking. We'll talk shortly about how that and other disconnects can be addressed using third-party solutions. Just showing here then the mapping of some of the basic types. Again, these map quite seamlessly. There are a few places where this mapping isn't quite so seamless, including, for example, as shown here, where we need to say pass a Swift int to shared Kotlin code and have to use this int32 wrapper. And lastly, some examples of collection types being mapped: list to array, set to set, and map to dictionary. A small example then of calling KMP code that returns a Kotlin list, which can then be assigned directly to a Swift array. The mapping is somewhat less straightforward if you need, for example, to pass a collection from Swift to Kotlin, but there are ways to do that. We mentioned some of the disconnects that exist when using the default approach to mapping between Swift and Kotlin. And one popular third-party solution that's emerged to address that is Sky, standing for Swift Kotlin Interop Enhancer. It's one of a suite of solutions that TouchLab have developed for KMP that have become indispensable. Included in what Sky supports are enums, sealed classes, as we mentioned earlier, default arguments, global functions, overloaded functions, and coroutines interop, which we'll talk about in more detail in the concurrency section later. So starting off with the example of sealed classes. These are, of course, quite an important part of the Kotlin language, frequently used, for example, for encapsulating, representing UI state as shown here. And a key aspect of what they provide is exhaustivity checking, which we don't, as mentioned, get in the default mapping that Kotlin Native provides. With Sky, this onenum function is automatically generated for us, which allows that check to occur. And we see it here, for example, in Xcode, if we try to remove one of the cases, resulting in this switch must be exhaustive error. Another small example is global functions. Without Sky, we have to prefix the function in Swift with the Kotlin file name. Sky removes the need for that. I mentioned earlier that existing Swift Kotlin interop is done through an Objective-C bridge. With Swift export, JetBrains is working to provide direct bindings. It's very exciting to see this develop. And speaking of which, I definitely recommend going to Pamela Hill's talk, which is up next here. She'll be talking, among other things, about the work they're doing on Swift export. Next up, concurrency. So just to start by giving some basic background on the structured concurrency functionality that we now have on both Android and iOS, before we talk about interop between them. This is a really powerful capability that allows us to write async code in a way that's easy to read, and also allows a more deterministic, structured approach to error handling and cancellation, for example. A key enabler of this is the ability to have code that can be suspended at particular points and resumed later. Swift supports these capabilities through the likes of tasks, async functions, and async sequence, and Kotlin similarly through coroutines, suspend functions, and flows. And a very important aspect of this is how invocation of code like this can be tied to the UI lifecycle, thus allowing, for example, automatic cancellation when a view disappears. So just a few small examples of how we would invoke async code in Swift and Kotlin. We can invoke from a function that's marked as async in Swift or suspend in Kotlin. We can also create a specific task in Swift, and similarly in Kotlin, create a coroutine from which it can be invoked. We can also tie the invocation of async code to our UI lifecycle on both platforms, along importantly then with automatic cancellation when the UI is no longer shown. We use the task view modifier in Swift UI for this, and can use, for example, launched effect in Compose. And showing examples of async sequence in Swift and flow in Kotlin. We use for-await in Swift to iterate over the values, and use collect in Kotlin to do the same thing. And also then a few examples of some of the operators supported. Firstly, using map to convert each value to a separate case version, and again iterating over the result in the same way. And then filter, for example, filter on a particular string, again in a very similar manner. Okay, now I'm going to talk about some of the concurrency interop options we have available to us. We'll briefly cover the limited default behavior we get out of the box with Kotlin Native, and then talk about a few third-party solutions that have become established to support this interop. So by default, Kotlin suspend functions are represented as Objective-C methods with completion handlers, or callbacks, which can be called from Swift as async functions since Swift 5.5. They do have some limitations, though, such as, for example, the fact that cancellations are not propagated. So I'm not going to focus too much on this approach. As I said before, there's third-party solutions that are generally used these days to provide concurrency interop, as we'll see shortly. Just to mention that the official guidance from JetBrains is also to use these third-party solutions, such as KMP native coroutines and Sky. And as mentioned before, both of these libraries support proper cancellation of coroutines. By the way, we're focusing here on interop with the Swift structured concurrency capabilities that were introduced in Swift 5.5, as they map quite nicely to the, how structured concurrency works in Kotlin. There are other libraries. There are, through these libraries, ways to support other iOS concurrency frameworks, such as Combine and Oryx Swift. First of these alternatives is the KMP native coroutines library. It was one of the first solutions created for providing interop for both suspend functions and flows. For suspend functions, we just need to annotate our Kotlin functions with @native coroutines, and then use, in Swift, use the library's async function to invoke, and can use then with Swift's await. Likewise with flows, in this case using the library's async sequence function to convert the flow to a Swift async sequence, and then can use Swift's for-await to iterate over the values collected. Next up is convert KMP observable view model, from the same author, by the way, as KMP native coroutines. This is a library that was previously known, by the way, as KMM view model, if folks were familiar with it. It's now described as a library to use Android X Kotlin view models with Swift UI, given the availability now of the KMP version of Jetpack view model library. And a key aspect of what this offers is the ability to expose Kotlin state flows, for example, as Swift properties that can be directly observed in Swift UI, as we'll see next. And this is an example of one of the shared Jetpack view models in the bike share project. In this case, exposing the list of countries we are displaying. We're using our repository class to get the list of countries, doing some transformation of that information, and exposing then as a state flow. This is how that's consumed in Swift UI in the iOS client. We instantiate the view model we saw in the previous slide using the @state view model property wrapper provided by the KMP observable view model library, which then allows that country list state flow from our view model to be observed directly here as a Swift property. And any change to that will cause our UI to be recomposed. As with KMP native coroutines, Sky also supports concurrency interop with Kotlin, showing here again how we'd invoke a Kotlin suspend function from Swift. With the approach that Sky takes using KSP, it can provide a more seamless interaction from Swift, as we can see here, with no additional wrapper needed. And then likewise for consuming Kotlin flows from Swift. We have a Kotlin state flow shown here, and can then use Swift's for await to collect the values from it. Another related piece of functionality that Sky provides is the ability to observe Kotlin flows in Swift UI, as if they were Swift properties. So quite similar to the functionality that the KMP observable view model library provides. Here we're observing in Swift UI the UI state flow from our Kotlin view model. And again, the UI will be recomposed if that changes. Next up, we're going to outline some patterns for using Swift in shared Kotlin code. So to start off with, a key enabler for this is the ability for a Swift class to subclass a Kotlin interface, and that implementation then to be passed to and used from shared code. That approach then is the basis for most of the interop scenarios we'll be describing. Starting off with a small example from the Firebase Vertex AI sample I have. This is a Compose Multiplatform application with most of the code shared between Android and iOS. Here we have an interface, generative model, defined in common main in our KMP module. In this case, being used to generate images using the Firebase Vertex AI. And this is the implementation on Android using the associated Firebase Vertex Android Gradle dependencies. It creates an image model using that library, and from that generates an image using the supplied prompt. And we can implement that same interface in Swift code, this time making use of the APIs from the Firebase Swift package to do the same thing. Note we're using Sky here, which makes the concurrency aspects of this quite seamless. We override the suspend function in the Kotlin interface with an async one in Swift, and can use Swift's await when invoking Firebase API. We're also making use of a helper function in shared code to convert the result to a Kotlin byte array. And then this is an example of how we can provide that Swift implementation to our shared code. In this case, we're providing it when we initialize the coin DI framework from Swift iOS code. That instance then becomes part of the coin object graph, and then is what is injected into common code when running on iOS. And here we can see that generative model instance getting injected into the view model in common main. Coin will inject the platform-specific instance of this, depending on the platform we're running on. And then showing compose code using coil to display the generated image. And again, this is in common code. Another common example is Firebase Analytics. And again, we define an interface in shared common KMP code, along with an Android implementation in our Android main source set. Again, using the Firebase Android Gradle dependencies in this case. And then implementation in Swift, making use again of the Firebase Swift package, and again, we'll pass this instance to shared code. In this case, we're using the Kotlin inject DI framework, passing in the Swift instance when creating the Kotlin inject component from iOS code. Using override here provides a similar mechanism to ensure this instance becomes part of our object graph when running on iOS. A small example from the confetti sample, using decompose component in this case. Here, we're actually providing the Swift implementation as closures, which again can be used from shared code. Another interesting approach that's emerged recently is the Swift package manager for Kotlin Multiplatform plugin, quite a mouthful. It provides the possibility, in certain cases, of actually consuming a Swift package from iOS main code. Next, we're going to talk about some of the UI interop options available to us when using Compose Multiplatform on iOS. We'll talk about how expect actual can be used again here for providing platform-specific implementations in shared code. We'll then give an overview of UI kit-based interop that's available, and how this forms the basis for allowing both consumption of Compose code in SwiftUI and SwiftUI code in Compose. By the way, for those who aren't aware, UIKit was the predecessor to SwiftUI and was the primary UI framework on iOS when Kotlin Native was originally being developed, so it still forms the basis for any UI interop. So first, a use of expect actual. So this is, in this case, the interop is done already for you using this approach in the increasing number of CMP libraries out there. For example, this is from the Kscan barcode scanning library from Ismail Mohammed, a colleague of mine at Kraken. Under the hood, this uses MLKit on Android and AV Foundation on iOS. This, by the way, was functionality Ismail developed to work, and we were very happy then to see it open sourced as its own library. @scanner view composable is defined as an expect function in common code. And then we have Android and iOS specific implementations, using, as mentioned, MLKit for the implementation on Android and AV Foundation on iOS. But again, consumers of scanner view, writing compose code in common main, are abstracted from these platform differences. As mentioned, Compose Multiplatform is interoperable with the UIKit framework. We can embed Compose Multiplatform within UIKit code, as well as embed native UIKit components within Compose Multiplatform. And by combining this then with SwiftUI's own UIKit interop, we can in turn provide a way to consume Compose code in SwiftUI and vice versa. A key component we're going to be dealing with when performing that interop is UI view controller, which is defined simply as an object that manages a view hierarchy for your UIKit app. So these are the key UIKit-related classes that Compose Multiplatform and SwiftUI provide to allow us to implement that interop, based on using that UI view controller object as a bridge. For Compose Multiplatform, we have Compose UI view controller. It's a CMP function that wraps Compose code in a UI view controller. And UIKit view controller, which supports the reverse, allowing inclusion of a UI view controller in a Compose view. And we have similar symmetry for SwiftUI with UI view controller representable, which allows including a UI view controller in SwiftUI, and UI hosting controller for wrapping SwiftUI as a UI view controller. I'm going to be saying UI view controller a lot, by the way. Lots of moving parts that will hopefully become clear as we work through some examples. And another view of these same classes here, showing the interop options they enable, using SwiftUI's UI view controller representable and CMP's Compose UI view controller to allow consuming Compose code in SwiftUI, and similarly using Compose's, or CMP's UIKit view controller and SwiftUI's UI hosting controller to allow consuming SwiftUI code in Compose. So let's firstly look at an example of how we can consume Compose code in SwiftUI. This is our main SwiftUI view. It includes Compose view, which is what will ultimately wrap around our CMP code. And that Compose view is a UI view controller representable, which allows including a UI view controller in SwiftUI code. And it does this by invoking main view controller in the shared KMP code from this make UI view controller function. And this is that CMP main view controller that in turn uses Compose UI view controller to wrap Compose code and return a UI view controller to the invoking SwiftUI code. And this approach is the basis for most scenarios where we want to consume CMP code in SwiftUI. Where things get a little more complicated is where we want to consume SwiftUI in CMP code. By the way, has anyone had to do that in their projects yet? Do the reverse? OK, a few. It's fun. And this is usually enabled through use of what's shown here as a native view factory class. This is a Swift class that implements a Kotlin interface and is responsible for creating SwiftUI views that Compose can use. The general approach here is the same as we mentioned earlier for consuming Swift code in shared KMP code, with an instance of that view factory being passed to and used from shared CMP code in this case. So I'm going to illustrate this using this example from the People in Space sample, where we're showing the position of the International Space Station. Here we have an outer SwiftUI shell that just basically includes a title bar. That in turn uses Compose for the content area, which in turn uses SwiftUI for the map. This is a somewhat of a contrived example, but is designed to hopefully clearly illustrate the various moving parts needed to allow implementing something like this. So the first part, consuming the Compose code in SwiftUI, is much the same as we saw in the earlier example. We have our outer SwiftUI view, that in this case includes a navigation view with a title bar. That view also includes ISS position content view controller, which will wrap our Compose code. Again, that's a UI view controller representable, which invokes ISS position content view controller in shared CMP code. That Kotlin ISS position view controller then, in turn, uses CMP's Compose UI controller to wrap the shared Compose code, ISS position content in this case, as a UI view controller, which can be included in SwiftUI. Note we're also passing down an instance of the native view factory we mentioned earlier. More about that shortly. OK, now going in the other direction. This is that ISS position content composable. It has some basic UI for showing the position of the International Space Station in Compose text views, and also includes an ISS map view composable, which will ultimately wrap around our SwiftUI map. An ISS map view, in turn, uses UIKit view controller to allow including a UI view controller in Compose code. That's going to delegate to the native view factory to create that UI view controller, which will in turn wrap the SwiftUI map. Note also that the view model we passed down from SwiftUI is being passed back up. It contains the position information which we'll need to show on the map. OK, we're nearly there. We're back up in Swift code again, and this is the native view factory and the create ISS map view function we just invoked from that Compose function. That's going to use SwiftUI's UI hosting controller to wrap the SwiftUI map implementation and return a UI view controller, which can be included in our Compose code. And finally, we have that SwiftUI map view. Note that we're using Sky's observing here to observe the position information from our view model. OK, that was a lot to take in. Hopefully, this provided at least a high-level awareness of what the moving parts are when implementing CMP interop like this. Alternatively, you can use Compose Swift View from TouchLab, which is another approach to implementing this, abstracting you from some of the details we just showed. OK, finishing this section with a small example of how common Compose Multiplatform adaptive layouts work equally well on iOS. This is the My Mac designed for iPad version of the Confetti CMP app. And you can see here a small example of how we can easily use the CMP adaptive libraries to dynamically switch between different layouts depending on the screen size. Next up, I'm going to talk a little bit about how we can run background tasks on iOS in KMP CMP apps. So there are two types of background tasks on iOS. BG app refresh task for short duration tasks that expect quick results, whereas a BG processing task is for tasks that might be time consuming, such as downloading a large file or synchronizing data. Has anyone here, by the way, had to do background tasking in iOS? OK, a few poor hardy souls. Showing here then how we firstly need to enable these capabilities in Xcode, and also how identifiers for any task we create need to be added to the project's info.plist. Starting off by showing a small example then of how we can, say, run a nightly refresh, triggered from SwiftUI using relatively new background task view modifier, but invoking then shared KMP code to do the work. When the app goes into the background, we schedule the refresh. That's done using this schedule data refresh method here, using BG task scheduler to schedule the request. Note that refresh data string shown here is the identifier we added to the info.plist. Very important to remember to add that. And then showing shell of the shared Kotlin code that the background task is invoking. Another approach is to create and schedule the tasks in iOS main in shared KMP code. There's a nice example of doing this, by the way, in Chris Baines' TV sample. And we're also doing something similar for a CMP project at work. Another useful API we can use in iOS main is begin background task with name. This allows us to mark the start of a task that should continue if the app enters the background. We also get notified if our remaining background time is running out, and can, for example, schedule a background task if that happens. Next up, we're going to look at some of the testing options available to us in KMP and CMP apps. These options include running KMP unit tests, CMP UI unit tests, Swift tests that invoke shared KMP code, and also wanted to show an example of a nice UI testing framework called Maestro that we can use to test both our Android and iOS CMP apps, for example. So first option here we have is running unit tests in common KMP code from our common test source set. These can be run then for the various platforms we're targeting. Note that we can also add, for example, iOS test source set here if we want to run iOS tests that need to test code that's in iOS main. A very nice capability that we also now have is the ability to run CMP UI unit tests from common test, also with option to run on different platforms. Another option then, depending on our requirements, is to run Swift tests that in turn invoke shared KMP code, as we're doing here in the Confetti project. And lastly, Maestro, a really nice UI testing framework that wraps around UI Automator on Android and XCTest on iOS. We can run the same scripts for both iOS and Android CMP clients, for example, with option then to run certain steps for each platform as needed. Another quick show of hands, anyone using Maestro here? Okay, yeah, that's a good number. And just a small example of Maestro test running here with the Confetti iOS application. This test automatically scrolls to the session title we're looking for. Eventually. Taps on it, asserts certain information is visible, and then navigates back. Next up, a few items related to developer experience. Yet another TouchLab tool that I'd recommend using is Xcode Kotlin. This is a plugin that allows browsing and debugging Kotlin code from within Xcode. Here we see, for example, a case where we've added Kotlin source to Xcode and have been able to set breakpoints in Kotlin code and view variables, etc. Really useful tool to have. Next, showing how we can view documentation that's in our Kotlin code from within Xcode. We just need to ensure that we set this option in our build file, after which we're able to see the documentation as shown here. In this last section, we're going to cover some topics around the building, packaging, and publication of iOS apps built using KMP and CMP. So there's typically two main approaches used for the building and consumption of KMP shared code. The first one here is usually based on a single repository containing both the shared and the client code. In this case, we build the iOS framework directly and consume it within the Xcode project. And the building of the shared code as an iOS framework is triggered through an Xcode run script like this that uses KMP's embed and sign Apple framework for Xcode Gradle task. The other approach is typically used where there's separate teams for the clients and the shared code, and usually involves separate repositories for each. Here, a Swift package is created from the shared code and published to a remote repository, along potentially with use of some cloud storage for the XC framework zip file that's part of the package. That package can be added then to an Xcode project using, for example, the GitHub repository URL that the package is published to, as shown here, for example, with the bike-share Swift package repo. The Swift package in this example for the bike-share project was built using the Multiplatform Swift package plugin. The plugin automatically creates the associated XC framework and package.swift files. The publication of these artifacts, though, needs to be managed separately. Another solution that many teams are now using for this is K-Bridge, or Cambridge as it's known, from, you guessed it, TouchLab. This also creates the XC framework from the shared code, but also supports a range of options for managing the publication. Okay, next up, umbrella modules. Typically, we need to expose a single iOS framework. But what do we do if the shared code is split across multiple modules, as is frequently the case? The solution generally recommended here is to create what's called an umbrella module, for which a single framework is built, but includes code from other modules, as shown here. Now I'm going to talk a bit about building, publishing iOS apps in CI. Folks might be familiar with using Fastlane for Android, but it also has a ton of really nice iOS-related integrations as well, and we'll show a few examples here. Another quick show of hands. How many people here are using Fastlane? Okay, and how many people are using on iOS? Okay, good few as well. That's great. What we typically want to do is build, sign, and publish the iOS app to App Store Connect, initially to test flight for internal and beta testing, and then to production. So Fastlane provides a nice option to build the IPA file that's needed for publication, as shown here. And then a task, for example, to publish the IPA file to test flight. And an important requirement when building, publishing iOS apps is, of course, how we sign them. And Fastlane provides a very nice option for doing this using a relatively new capability called Match. With this approach, we add our certificates and provisioning profiles to a dedicated private GitHub repository. And Match then provides a convenient way to both distribute these across the team and also use in CI. And a small example then of using Match in CI to automatically sync certificates that can be used as part of the build. So today, we talked about various patterns and capabilities that we can apply when using Kotlin and Compose Multiplatform on iOS. We covered the basic interop capabilities we get by default. These, as we mentioned, have some limitations, and we gave some examples of how these can be addressed using the Sky framework. And also mentioned the promising Swift export work being done by JetBrains. Similarly with concurrency, again, we covered how a number of third-party solutions can be used to address the limited interop support we have there as well by default. Next, we outlined various patterns that can be used for including use of Swift in KMP shared code. And likewise then for Compose Multiplatform, showing various interop options available for including Compose in Swift UI and vice versa. We talked about background work on iOS, some of the KMP, CMP testing options available to us, and a few items related to developer experience. We finished up then with some info on build, packaging, and publication, again focusing on iOS aspects of this. Thank you.
Hello.
Hello.
I tried to make a library in Kotlin Multiplatform and use it in iOS project with Swift Package Manager. But in this library, I have a lot of resources like images or font file. And Xf Framework cannot package these resources. Have you a solution for embed resources into a library can be used in iOS code?
It's not something I've specifically done, though I have seen some references to people. I know in Gerard's talk earlier about JSON forms, he was talking about how they're using Compose Multiplatform and they were packaging it into an XC framework. It might be worth checking with him. I'm not too sure. I think there was resources involved in that. Might be a topic maybe for Pamela to talk later. I'm not sure if that's something. But sorry, yeah, it's not something. Yeah, I've done it in a few places where I've created Swift packages using XC frameworks, but I can't remember. I think they were mostly KMP, they weren't CMP. You're talking about sort of Compose Multiplatform where you have, is it where you have Compose Multiplatform resources or just resources in general?
I'm sorry, can you speak
Was it a KMP or was it a sort of CMP library? Was it like a CMP library where you were?
It's a CMP library.
Okay. Yeah, no, that's interesting. I haven't done it myself now, but I believe, I don't know if Jared's here, he might be able to answer, but this might be worth checking with him. Jared Paligot gave a talk earlier from Decathlon about a CMP solution they're developing. But yeah, sorry.
Hello, thank you for the presentation. I just wanted to ask if you found a solution to get the Compose previews working for the multi-platform setup, basically.
Okay, that's an interesting area. So I think with the latest, that should work with the latest. So you could use it from Android main. You could previously do that. Yeah. But in the latest Canary, I believe, that should be working. And I know it is working, actually. I think we tested that work, actually. So the latest Android Studio Canary, you can use previews in common main for your shared composables.
Okay, thank you.
That's definitely it. Okay, thank you very much. Merci beaucoup.